going through problem 3.30 of Taylor's Classical Mechanics. This is a chapter 3 problem on angular momentum. And the problem says to consider a rigid body rotating with angular velocity omega about a fixed axis, to take the axis of rotation to be the z-axis, and using cylindrical polar coordinates to specify the position of the particles from alpha equals 1 all the way up to n that make up the body. And we want to first show that the velocity of a particle alpha is p alpha omega. And that is in the phi direction. You may be more familiar with cylindrical polar coordinates in r, theta, z. That's going to be the same as p phi z, which is the coordinates that we're going to be using for this example. Alright, so we'll start by showing that velocity. We can just model the equation here. We know that it's going to be rotating around the z-axis. So in p and phi, we're going to have something that looks like this. We're going to have a particle. And it's going to be moving around that z-axis, which you can imagine is here in the middle, coming up out of the page. And that particle is moving in the phi direction. So the distance here from the z-axis is p, and it's moving in the phi direction. If we imagine it moves by some infinitesimally small amount, that's going to be d phi. And we can imagine that the distance that it moves, so dr, and we'll call that tangential because it is moving in a circular path here, though the distance it's moved will be tangential to that. So the distance it moves tangentially, infinitesimally small amount, will be equal to p d phi. Now if we divide this by dt, we will have dr tangential over dt is equal to p d phi over dt. And this is because we're taking p to be constant. We're saying that it's not varying for this particle over that path that it's taking. So we're able to leave that out of there. So, and this may look familiar. We have a derivative of position with respect to time is velocity, p, and derivative of phi with respect to time is omega. And I'm pretty sure that's what part A was asking for, to show that velocity was going to be equal to p omega, and we can say the alpha equals p alpha omega. So that answers our part A. Now, moving on to part B, we want to show that the z component of the angular momentum of a particle alpha is m alpha p alpha squared omega. So we're trying to show that the z component is going to be m alpha p alpha squared omega. We know that angular momentum is r cross p, and that's our momentum p. So we know that that is r cross p. For our position vector, we are going to have p times that polar unit vector plus z times the polar z vector. And for our momentum, we know that we just found that our velocity is p omega. We know that momentum is mv, so mass of alpha, v of alpha. If we want to do it in that way, we'll leave it without the alpha on there for now. So it's going to be mv, which is the same as m p omega. And we're going to put the phi unit vector because it's moving in that phi direction as we showed up here. So by taking the cross product of this, we're going to be able to see the components of our angular momentum. So L, our angular momentum, is going to be equal to R cross P going to be equal to the determinant of P, phi, z, and we will take our components to be P coming from this position vector up here, 0, z, and coming from this momentum vector, 0, mp omega, and 0. So taking this determinant, we're going to get times mp squared w we are actually going to get negative mpwz for this polar unit vector. We're going to end up with 0 for the phi, plus 0 phi, and that's where we're going to have our p squared omega. So our momentum vector is going to look like mp squared omega z minus mp omega z p hat. And we're asking for that z component. So we're only concerned about this part. So that angular momentum, the z component, is equal to m alpha p alpha omega and LZ equals m alpha p alpha squared omega. There's exactly what they wanted us to show. And that was part B. So part B says show that the z component of the angular momentum alpha of a particle alpha is m alpha p alpha squared omega. So we did that. Now we need to show that the z component of the total angular momentum can be written as LZ equals IW, where I is described by this equation right here. So LZ equals IW, where I summing from 1 to n. And we know, this was part B, we know that that total angular momentum in the z direction is going to be equal to the sum from alpha equals 1 to n of those individual angular momentums. And we can call that alpha z as well. And that's also going to be equal to the sum from up here, our part B answer, from alpha equals 1 up to n, of m alpha p alpha squared omega, which from this we can see that if we're saying this is equal to I omega, that moment of inertia, times the angular velocity, this part must be our I. So therefore we have I equals alpha equals 1 to n to m alpha p alpha squared.